So when I first looked at this picture, I thought, oh good, an energy problem. You're going to snap that string, it'll swing down to the bottom, find out what the velocity is at the bottom. But then I read it more carefully. The problem says, compute the reaction at the pin O just after the cord AB is cut. So it's not spinning down. So what this means, it's an equation of motion problem again. So that means drawing a free body diagram. So here we go. We're going to draw that loop, everything in the loop. You've got that 30-pound sphere, and I've drawn that in there, and there's a 30 pounds. The rod is 10 pounds, and it's a slender rod, and it's at the middle of that 2 feet. And we cut through the reactions, so there's Rx and Ry. Note there is no tension going up because this is just after we cut it. And so then equals MA. So on the other side, what you have is you have M of the sphere times acceleration going down, M of the rod times acceleration going down. And you know that the acceleration of the rod is the alpha of the rod times the distance to the center of gravity of the rod, which is 1 foot. So that's why the acceleration of the rod is 1 times alpha. You know the acceleration of the sphere, similarly, is the distance from the pin, which is 3 feet, times alpha, and that's the acceleration of the sphere going down. In addition to this, you have the I of the sphere times alpha and I of the rod times alpha. And we've talked about this. Anytime a rigid body rotates, every spot on the rigid body has the same omega and the same alpha. So we don't have to have alpha of sphere, alpha of rod. They're all part of the one piece, and so we're just writing alpha. So you can see the right-hand side has just alpha. And real quickly, there are 3 unknowns here. Let me point them out. There's the alpha, which is unknown. We've gotten rid of the other 2 accelerations through kinematics already. And then there's the Rx and the Ry. Okay, there is also the acceleration, centripetal acceleration going in of mv squared over rho, but since it's cut, just after it's cut, it's still at rest, the velocity is 0, so mv squared over r is 0. Okay, so let's do this. If you sum the x components, you have, I guess technically you have minus rx going to the left, if I take to the right positive, and there are no x component accelerations on the right hand side picture, so it's 0, so Rx is 0. We're going to take moments someplace clever. So to me the clever place is to take the reactions about the pin, to get rid of both of those reactions. So on the left hand side, taking moments about the pin, counterclockwise is positive. That 30 has a moment arm of 3, and that 10 has a moment arm of 1. Okay, the right hand side, let's carefully take the moments around the pin on the right of everything. So you have MA of the sphere, so M times 3 alpha, and its moment arm, its distance from the right is 3. You have MA of the rod, which is M times 1 alpha. A of the rod is 1 times alpha times its distance from the left, which is 1 foot. And then you also have the 2 moments, I of sphere times alpha plus I of rod times alpha. And then you can immediately just solve that for alpha, plug in the numbers. Of course, you have to calculate M and I and all those sorts of things. But it doesn't want to know alpha. It wants to know what the reaction is. So we already have that the X reaction is 0. We need to get the Y reaction. So the sensible thing to do is take the Y components of everything. So on the left-hand side, you have minus 30 coming down, minus 10 coming down, and the reaction Ry going up. And on the right-hand side, you have minus m sphere times A of the sphere, which again was 3 alpha, and minus m of the rod times alpha of the rod, which again was 1 alpha. Okay, and so solve for Ry, and this is what you get. And so that's interesting. Now, if it was statics, the reaction would be 40, but it's less than that because it's rotating down. And depending on what alpha is, this could even be negative. So there you go.